This video is going to show you how to run a multiple regression as well as a hierarchical multiple regression using JASP. The data we're going to look at in this example is looking at the effect of commercial and non-commercial TV viewing on body mass index in children. So we've got body mass index here, which is our dependent variable, which is just how heavy the child is. And then we've got hours of non-commercial TV exposure, so the number of hours of non-commercial TV they watch per week, then the number of hours of commercial TV they watch a week, and then we've got the age of the child and then the gender of the child, whether we've got a boy or a girl. So what we're interested in really is the extent to which these two variables predict body mass index. We also want to control for the effect of gender and age on body mass index. So it's a really straightforward analysis. We've got a continuous dependent variable and we want to see the extent to which these four variables are associated with body mass index. You can see we've got an extremely large sample in this example here, so we've got 1,087 children in this sample. So in order to do this analysis, we go to regression, and we just want a standard linear regression because our dependent variable is scale. Let's make some space. So if you use SPSS, you'll already be quite familiar with these. This is quite similar to what an SPSS user interface looks like. However, there's a few differences, and in fairness, it's a lot easier to use and a lot more straightforward to produce the statistics you want, which is one of the key benefits of JASP. So we've got our dependent variable here. Well, our dependent variable is the thing we're predicting variance in, which is body mass index. And then covariates, and these are just our predictors. And we just simply need to click across our predictors. And as you can see, the model builds as we add things to it. And this is essentially our model. So we've got our model summary, we've got the ANOVA table, and we've got the coefficients. So the first two tables are about all the variables taken together. This is essentially telling us how good this overall model is, how much variance of these variables taken together predict in body mass index. To make that interpretation, we can look at the R squared or the adjusted R squared value. We'll just look at the R squared today. You can choose either really. Adjusted R squared basically just makes a correction for the predictors in the model, so adjusted R squared will always be lower than an R squared. We're going to report R squared today, and that's just simply to keep it consistent with some other statistics that we'll do later on. So if you look at our R squared value, this gives us 0.023, and this is the proportion of variance in body mass index that all these variables taken together predict. And as you can see, it's only a very small amount, so this would be 2%, 2.3% of variance in body mass index is predicted by all these variables taken together. As you can see, if it's adjusted R squared, it's down from 2.3% just to 2%. However, that's just a rough proportion of variance. It's not very much variance, but this table here will tell us whether that is a statistically significant amount of variance in this sample. And what this gives us is an F statistic, our degrees of freedom, and the p-values. This will tell us whether we can say we've got a statistically significant model. And as you can see, we've got a highly statistically significant model. So this 2.3% is highly significant. And of course, this is largely a product of the fact we've got a very large sample size. The bigger the sample, the more likely it is that something's going to be statistically significant. So I think this is quite a neat way of showing the trade-off between probability and the size of an effect. If you judge this model based on this statistic here, it's highly significant, you've got a brilliant model. If you actually look at the amount of variance it's predicting, however, it's only quite a small amount of variance, and you'd probably expect that because body mass index is not going to be fully dependent on all these factors. We're not taking into account the child's diet and all factors that are likely to influence it, so you probably would expect only a small amount of variance. So you should always be very careful. It's a highly significant effect, but it doesn't predict that much variance. However, you can write up these statistics like this. So you could say the overall model predicted approximately 2% of variance in BMI. And then we can give our R squared, we can give our F statistic, along with its degrees of freedom and its p-value. So that tells us about the model. Overall, what's the model predicting? Of course, this doesn't speak to the individual regression coefficients of our individual variables. So does gender predict variance? Does age? Does commercial TV viewing? Does non-commercial TV viewing? Let's look at that. We want to look at this coefficients table here. So you'll see this gives us two forms of regression coefficients. It gives us unstandardized regression coefficients, which are reported with a standard error, and then it gives us standardized ones. It also gives us a t-statistic, and it's the t-statistic that's used to derive the p-value. So if you were to report the unstandardized regression coefficients, you must also report a standard error as well. This doesn't mean anything really without a standard error. The standardized one, or the beta, doesn't need a standard error or anything like that. It's fully standardized, and it's basically things in terms of z-scores. The standardized one's quite useful in terms of you can look at these and straight away you can see that this is the strongest predictor because it's the highest beta value. Then the next strongest predictor is this, because that's the next highest beta value. On the minus, that just means negative association. Then your next highest one is age of child, and non-commercial is the lowest. However, you can also report them as unstandardized and a standard error. Broadly, as a very rough rule of thumb, you want the unstandardized regression coefficient to be, at least twice the size of the standard error, then you're more or less likely to have a statistically significant effect. But, it generates a p-value for you, so you'd have to rely on those rules of thumb. But of course, it's quite a good rule of thumb for spotting errors actually in published papers, because you sometimes will come across a regression coefficient and a standard error in which maybe, like in this example here, they're almost the same as each other, yet it's got a significant p-value associated with it. That'd be indicative of an error in reporting. So that rule of thumb can be quite useful if you think some of the results in the paper look quite unusual. We can interpret all these in a relatively straightforward way. The only challenging one we've got here is the gender of the child. That's because we've just classified them as being a boy or a girl, and we've got a negative regression coefficient here. Obviously that gives us a negative beta as well. So the way you interpret that is relatively straightforward. We've coded males as 0 and females as 1. This means that, because it's negative, this means those coded as the lower number, so those coded as 0, have higher BMIs. If that was positive, that would mean those coded as the higher number, so females who are coded as 1, they'd have higher BMIs if that was a positive number. So simply, if it's negative, the group coded as the lowest number have higher scores. That's what gives you a negative regression coefficient in this example. If it's positive, that means the group that's coded as the higher number has higher scores. So in this case, because it's males coded as 0, females as 1, this negative regression coefficient means that the males are, in this sample, are heavier than the females. Age of child. So age doesn't have a statistically significant effect. Hours of commercial TV exposure has a significant effect, and hours of non-commercial exposure does not have a significant effect. And we can just write these up like this example below. So in this example, I just cover the two non-significant ones first. You can do it in any order really, but there was no significant association between age of the child and BMI. And we can report, in this example, I'll show you the unstandardized regression coefficients, its standard error, and the p-value. And nor was there an association between hours of non-commercial TV viewed and BMI. And we report unstandardized regression coefficients, standard error, and the p-value. There was a significant association between gender of the child and BMI, and with boys having greater BMI than girls. And you'd want to make that statement about which group has higher scores than the other, make that very clear. And finally, there was a positive association between hours of commercial TV viewed and BMI. If that was a negative association, That would mean the less commercial TV you watched, the greater your BMI was. In this example, it's positive. That means more commercial TV viewed, the greater the BMI of the child in this example. And we can write this up. So that gives you pretty much a full write-up of this. There's a few other things that you can do as well. If you click on statistics here, we could also ask for confidence intervals. And this gives us a confidence interval for our regression coefficients as well. So that gives us our measure of precision of the estimate. And we could just add these to our write-ups as well. So after we report the p-value, we can also give our confidence intervals for this. I'd recommend doing that as well. It's always good to give that information to the reader as well. The other thing that we could ask for as well, we could ask for descriptive statistics, which gives us a mean and a standard deviation and a standard error for our variables. Of course, for gender of child, that statistic's completely meaningless because the data is nominal, so it doesn't lend itself to a mean and a standard deviation. The other thing that you could ask for as well is collinearity diagnostics. So the collinearity diagnostics appear here. And you can see it says tolerance and VIF, and one's just the inverse of the other. VIF stands for variance inflation factor. So let's look at the variance inflation factors here. Basically, if it's 1, it means there's no issues with multicollinearity at all. If it's above 3, then you probably want to look into your variables a little bit. There seems to be a problem with multicollinearity. That's a violation of one of the assumptions of the regression analysis. We won't go into that in too much detail here. This is more a guide just how to run these analyses. Above 5, you're in serious trouble. Above 10, terrible trouble, and you'd probably want to be removing variables, because what it basically means is you've got 2 variables that are so highly correlated, it means that there's going to be problems with your regression coefficients, and you won't be able to really interpret your model at all. So you'd want to look at the variables that are causing problems and remove them from the analysis. So that gives you a pretty clear write-up of the model. I'm just going to get rid of collinearity diagnostics now, just to make the model simpler. There is another feature that we can do though. So if you look at these variables, we've got gender and age, we've got some really basic demographics, and then we've got our TV exposures. These are things that we are particularly interested in. What we can actually do is tell JASP to break our model down into 2 parts. So we go to model, and as you can see it says here, add to null model. So basically what we can do, we can say, okay, we want to break our model into 2 parts, and we want to control for these factors and see how much variance these 2 factors predict after controlling for these. So we just simply tick and tick. So now we've got model 0, our null models. These are variables we're controlling for. Gender of child and age of child in the null model. And then we've got model 1 is hours of commercial TV exposure and hours of non-commercial TV exposure. You can see here it's now broken our model into 2. We've got R squared, adjusted R squared, and it's all been broken down. Now if you click here, R squared change, it gives us much more information. So now we can see we've got an R squared change. So this is the amount of variance that model 0, gender and age predict. It's got an F statistic, it's got degrees of freedom and a p-value. So age and gender predict a significant amount of variance in BMI. It's approximately 0.9% of variance, and we can report these statistics. Now, after controlling for this 0.9% of variance, what we can see is that model 2 predicts an additional 1.4% of variance, and this is statistically significant. We've got our F change statistic, our degrees of freedom, and our p-value associated with it as well. And remember, just like before, we've got highly significant results coming through here, but quite a small amount of variance explained to make sure that you don't overblow these findings. Oh, it's highly significant, when we know it's actually a very small amount of variance. You can see that the R squared here is that plus that gives that, and that's the total amount of variance that's been explained. From the ANOVA, you can see this is the ANOVA for model 0, and that's actually the same thing as the F change, same p-value, same degrees of freedom and so on. This is the full model, so this is everything all together, and you'll note that this F value is the same F value we reported before. That's just the statistics when everything is considered together. The coefficients table also changes. Generally speaking, when you write these things up, you can just report them from the full model. So this step approach really is about the model rather than the individual regression coefficients here. So I'd always just write up these ones here. You'll note, there's some minor changes. So gender of child in the full model with everything in it is 0.083. In this model, 0.080. So it's some minor changes in this case, and that's because in the regression model, when you add these variables, obviously this is also going to influence the effect of this variable in some way. To write this up, you can write it all up in continuous prose as before. And certainly you'd still write up that the overall model predicted approximately 2% of variance in BMI, and you can report your R squared along with its ANOVA. Then you could also write up the step part of it. Step 1 predicted approximately 0.9% of variance in BMI, given the F change, its degrees of freedom, and the p-value. And then say step 2 predicted an additional 1.4% of variance, F change, degrees of freedom, p-value, and so on. However, what you could also do is put it into a table that looks like this. So this table covers the R squared values, covers the F change values, and the regression coefficients. In this example, just to show a different way of doing it, this has got the beta values, so the standardized regression coefficients along with the p-value. So you can see the way this is set up is a cumulative and a simultaneous model. So cumulative is showing you the breakdown of the R squared statistics and the F changes to show the amount of variance each step predicts. The simultaneous model all comes from the final part of the table when all the individual regression coefficients are considered together. So this table gives a really nice breakdown of the entire model, also shows you the association between each of the individual predictors and the dependent variable when we consider everything in a single model together. So I think this is quite a neat, straightforward way of communicating this information in a relatively straightforward table that gives a reader good understanding of not only how much your model breaks things down, the values of each individual predictor as well. Currently, unfortunately, JASP only gives you 2 steps in the model, gives you a null model and then predict additional variance from that. Hopefully this will change in the future and you'll be able to add more steps to it, because that may be particularly useful for things like moderation. But as it is, this is a really neat interface that gives us a lot of useful information about our regression model, and certainly it would be sufficient for undergraduate and indeed a lot of postgraduate analyses.